Hello students, we are going to discuss about feedback control of system with dead time and inverse response. First we are going to discuss about system with inverse response. We have seen different type of system response. So far first order system, second order system with time lag, etc. Another type of system can also be classified with this typical step response pattern, system with inverse response. It is essentially a system whose transfer function is having a 0 on the right half of the plane. This type of system is called no minimum phase system. Example of a system with the inverse response, so that is boiler drum. This figure shows that boiler drum. Before going into the detail, let us consider a simple example of a system with the inverse response. Consider the dynamic characteristics of a boiler drum and a water tube boiler of a steam power plant. High pressure feed water is pumped to the drum. Water from the drum circulate through the boiler tube, get heated and is converted to steam. This steam again comes back to the drum and subsequently is taken out through the steam flow line to the turbine. So the drum is filled up partially with water and partially with steam, both at high pressure. It is very important to control the water level of the drum at a desired level by controlling the feed water flow with the varying demand of steam. The instantaneous level of water at the boiler drum is decided by the steam flow rate and the feed water flow rate, and it would reach a steady state when both are equal. Now suppose the steam flow rate suddenly decreases, the feed water flow rate remaining constant. At a first glance it would appear that the drum level should rise, but actually the drum level will initially drop for some time before it rises and reaches a steady value. This is because of first that drop in steam flow rate will initially cause the rise in steam pressure in the drum. Due to the rise in pressure, the bubbles present inside the water in the drum will momentarily shrink. This will cause the temporary fall in the drum level. Similarly, for a sudden increase in steam flow rate, the drum level will momentarily swell before it drops down to a steady state value. Are you clear? Transfer function with inverse response. So U of s is the load variable, C of s is the controlled variable. Process 1 transfer function K1 divided by 1 plus tau 1 s. Process 2 transfer function K2 divided by 1 plus tau 2 s. The overall output response can be written as C of s divided by U of s is equal to K1 by 1 plus tau 1 s minus K2 by 1 plus tau 2 s. So from these C of s is equal to, so take LCM here, 1 plus tau 1 s into 1 plus tau 2 s, the cross multiply K1 into 1 plus tau 2 s minus K2 into 1 plus tau 1 s. So the finally we get C of s is equal to K1 tau 2 minus K2 tau 1 into s plus K1 minus K2 divided by 1 plus tau 1 s into 1 plus tau 2 s into U of s. Are you clear? Okay. Next we are going to discuss about feedback control of system with dead time or Smith predictor. In chemical processes having large transportation lag can be difficult to control because the change in the set point or the load variable in the control system does not immediately reach the output variable for the process because of the effect of the transportation lag parameter or dead time. The transportation lag compensation method which was proposed by Smith. So that's why this is called Smith predictor or Smith predictor of the control system. In this method, the effect of the transportation lag is reduced on the control system. Open loop response to a change in the set point is given by Gp of s is equal to e power minus s into tau d into g of s. G of s is the overall transfer function, Gp of s is the process transfer function, tau d is the dead time or transportation lag. Thank you for your attention.